Can you see the shared content?
Yeah. So our next speaker is Sam Buchanan from Columbia University. He's going to talk about deep neural network and multiple manifold problems. Let's welcome.
Thank you for the opportunity to speak. Yeah, I'm a PhD student at Columbia University with John Wright. And John, so I'm presenting our joint work here. John presented this earlier as well. I hope that my talk will be able to shed a bit of light on some of the more technical aspects of the work and complement John's in that way as sort of a technical appendix talk, if you will. And this is also joint work with Dargo Bo and Tigran Wang. So I'm going to be presenting so the talk's based on a couple of papers. One we presented ICLR earlier this year, the other we just posted as a preprint. A lot of the notation and topics will be especially drawn from the second one. So if you're interested, I encourage you to check it out. As John, if you caught his talk earlier, was talking about, we're interested in trying to study a model problem for how deep neural networks can sort of provably classify data that have nonlinear low-dimensional structure. Trying to understand these interactions is maybe a path towards understanding how these networks work on practical data sets where this structure can be pretty ubiquitous. So the problem we're studying in this paper and that I'll present now, we're going to call the two-curve problem. And this is a binary classification task where the two classes are disjoint one-dimensional submanifolds of the unit sphere. And the task is like this. So you get capital N IID samples from some density that's supported on these two manifolds. The samples come with labels. And the task is for you to train a neural network with simple gradient descent and guarantee that after not too many iterations, this network is going to achieve perfect generalization. So this sort of strong sense of generalization where you perfectly label the two manifolds from finite samples. A couple of technical details on the data model in this problem before we get into more specifics. So in this paper, we're assuming that the curves are smooth, regular, simple, so they don't intersect themselves, also disjoint, they don't intersect each other. They're closed, so they're topologically circles. And for technical simplicity, we also have this assumption that they're contained in a cap of radius pi over 2. This is purely for technical convenience, and I hope we can remove it soon. So under these assumptions, I'm going to denote arc length parameterizations for the curves by superscript plus and minus x. And throughout, we're going to be talking a lot about two different measures of distance on the sphere and between points on these curves. So the extrinsic distance, I'll call it the angle, is like the spherical geodesic distance between points. And I'll also label the intrinsic distance measured in this arc length parameterization as d subscript m, and just declare it to be infinite if the points are on different components. The network we train here is especially simple. It's just a standard deep feed-forward neural network with ReLU activations. We're going to give it a Gaussian random initialization with the standard parameterization settings of the variances. And we're going to train with, so this randomly initialized constant stepping gradient descent on the empirical mean squared error from the n finite samples that we get. So the difficulty of a problem instance in this model, the nice thing about having the data with low dimensional structure is that we can summarize it in terms of certain geometric and statistical properties of the data. So I'll just summarize them quickly here with definitions and talk about some intuitions. The ones that will show up in our results. So we have curvature. This quantity here, I guess, is the intrinsic curvature, measuring how far away the curves are in a worst case sense from being great circles. We have a separation here. And so although I'm labeling this in the figure as the separation between manifolds, the way it's defined here, it can also measure sort of how simple the curves are. So how close they come to intersecting themselves. So it's sort of a self-separation measure as well. Something we'll need to state some results is also a count of, at a given point, how often points on the other curve can loop back, or the curve can loop back to itself. I'll just denote that by this clover symbol. And we'll also need to use some properties of the density. In particular, we assume for our analysis that the density is bounded below by a positive constant. And the theoretical question we can try to resolve in this nice model, trying to understand the interactions between the network and the data, is how do we need to set these simple architectural summary hyperparameters, the width, the depth, and the number of samples, relative to the geometric properties of the data in a way that we can guarantee the gradient descent succeeds in this problem. So to get into it, I'll just show our main result quickly, as John presented earlier. So the result just is pretty simple to state. If the step size is sufficiently small, And if you set the network depth to be a sufficiently large polynomial in geometric and statistical properties of the data, as well as a mild logarithmic dependence on the ambient dimension, and if you set the width and the number of samples to grow like sufficiently large polynomials in the depth, then very rapidly gradient descent will give you a neural network classifier that perfectly separates the two manifolds. So it's a simple result to state. Took some time to obtain. And I think something that may be interesting here, as far as I know, this is the first generalization guarantee for training deep networks to classify data with non-trivial, nonlinear low-dimensional structures. So the nonlinear qualifier is doing the work there. In the rest of the talk, I want to try to give some intuition into the proofs and tell a couple stories around how the different architectural hyperparameters are allowing us to solve the problem in our analysis. So first, I'll just mention the way we're proceeding in the analysis is using this neural tangent kernel regime techniques. So this is a regime where you set the network width to be sufficiently large such that all throughout training, none of the weights in the network change very much. And the final predictor that you get from gradient descent is equivalent to a certain kernel predictor with a kernel that's generated by this sort of taking inner products of gradients of the neural network at different points, evaluated at the random initial parameters. So this has been studied a lot in the theoretical literature, and it's led to some very interesting guarantees for neural network training. And like I was saying, I'll try to tell some stories around this, how this kernel plays a role in our analysis, and some potentially more broad technical contributions that we have, maybe of broader interest. So the first story is about the role width plays. In particular, it's a statistical resource. When the width is large, quantities concentrate well around their expectations, and that allows us to have a sort of deterministic quantities that we can analyze to prove that generalization and fitting proceed. And the depth plays the role in particular as a fitting resource. So when the network depth in our analysis is set large relative to how complicated the geometry is, it gives us an ability to fit better. Deeper networks fit more complicated geometries. And I won't have time to talk about all aspects of the proofs. Please, reach out if there are other things that you find interesting here. So first, the width story. The role that width is playing first and foremost in our analysis is it ensures that this random neural tangent kernel, which is our sort of random process, is uniformly close to its expectation over the initial random weights all throughout the training, the gradient descent training process. And sort of the figure at the right is showing some degree as I increase the width further and further empirically, I get better and better concentration of one trajectory of this random process around its infinite width limiting value. And so the result we prove here is sort of a new rates of concentration for this kernel. These are uniform rates of concentration. So the bound is a high probability tail bound that holds simultaneously for all inputs. And it holds in the regime where the width grows linearly with the depth. So as soon as the width is growing linearly with the depth up to polylog factors, as well as a polynomial dependence on the dimension. So just a couple quick comments on this result. Previous best results for these rates of concentrations for deep ReLU networks were shown by Aurora et al. In 2019. Their rates were quantity L squared over N to the 1/4 power. Their result is more general than ours. The network width doesn't need to be the same in every layer, but we've sort of sharpened these results here. And in particular, the results we have are essentially optimal. So Hanan and Nika have studied concentration of the neural tangent kernel in the case where the two points x and x prime are equal, so on the diagonal. And in that setting, they show sharp upper and lower bounds on the variance. If you integrate out this tail bound in order to get a bound on the second moment, you'll get something that matches up to log factors. And so we can sort of conclude as well that these bounds are essentially optimal, in particular as reflected to the depth. So that's all I'll talk about for the width story. And next, I want to talk about the role depth plays in the analysis. And for that, I need to introduce some notation around what we call the certificate problem. So I will, in the rest of the talk, use this theta kernel notation to denote appropriately scaled infinite width expected neural tangent kernel. And I'm going to use a bold theta to denote the integral operator that's associated to that kernel. So with that notation, the certificate problem, which is sort of abstract, but I'll try to interpret it, is to find conditions on the width and the depth, these two parameters, so that we can find a certain approximate solution to this specific integral equation here involving the NTK and the initial random network F sub theta 0. actually the initial random error, so that network minus f star. So we need to have a good approximate solution to this integral equation, and it needs to have a small norm. So that part is important. So just to try to put some context into this problem, I'm showing a figure at the bottom where I take a certain data set, the toy one from before, and I compute a discretization of the neural tangent kernel integral operator over that data set, and just sort of quantitatively invert it and plot what the certificate looks like. So one thing we can take away from this specific example is that, so it seems that in this case, the certificate is not totally regular. And in particular, it has these certain intervals where it takes on relatively large magnitude around points where the problem is somewhat harder. So in particular, points where the two manifolds come close to touching each other, or where the curvature is relatively large. And just unrolling a bit in the figure on the right, I'm taking the same certificate plot at left, plotting it in a chart for the two curves, and also showing two different traces corresponding to neural tangent kernels of different depths. So 10 and 100 are shown here. And what we can take away from this plot is that the norm of the certificate decreases as the depth increases. So both in sort of L infinity and in the average sense. So we get an intuition from this type of an experiment that depth can help in guaranteeing that a certificate is small, or that there exists a small certificate for the geometry. And we're going to try to unpack that further. So one minor simplification thing to note, is that, so this certificate problem, again, is kind of abstract here. If you're familiar with the neural tangent kernel literature, one point to make is that the existence of a certificate of small norm is more or less equivalent to the target function, this initial random error, having a small RKHS norm in the RKHS that's associated to the neural tangent kernel. So since in the neural tangent kernel regime of training, we intuitively have that the final predictor is equivalent to a kernel method with the NTK, it should come as no surprise that having a small RKHS norm, and by that I mean having a certificate exist of small norm, is very important for both optimization and generalization. So a bit more notation in the rest of the talk. So we can use the fact that we have this Gaussian random initialization for the initial parameters to guarantee that this kernel theta is rotationally invariant on the sphere. So in particular, we can find some function psi such that theta is equal to that function just composed with the angle function. And in the rest of the talk, so I'm going to simplify my life a bit. We do this in the paper as well. I'll work with a version of theta superscript circle, where I subtract off the value at pi. So that just makes the kernel concentrate a bit better. It takes value 0 at the largest possible angle. And we can phrase a corresponding certificate problem with this integral operator instead of the previous one. All that's changed is that we've changed the kernel here. We've subtracted its value at DC, if you will. And we show in the paper how a solution to this problem implies a solution to the original certificate problem. Okay, so just some intuition for why the certificate problem is hard. The natural thing to try to do to solve this problem, well, it's just a linear integral equation. So we'd like to try to diagonalize the integral operator theta. We can always do that because in this case, we have a lot of regularity on the manifolds. So we can find some, in particular, some non-negative eigenvalues and corresponding eigenfunctions such that the operator can be expanded in this way. And we'd just like to use properties of these eigenfunctions and eigenvalues in order to figure out, so how should the solution of the integral equation, the certificate problem, behave? What's challenging in this setting, so what you do normally, and what has been done to great effect in the literature, is so in certain highly symmetric geometries like spheres, you have that this theta operator acts convolutionally because the kernel is rotation invariant on the sphere. And as a result, sort of as I see it, you have closed form expressions for these eigenfunctions, which you can use to compute. You can compute estimates on inner products of any sort of function of interest with eigenfunctions, and you can figure out the eigenvalues and precise rates of decay for them as well. The difference in the setting we consider here, where we have nonlinear low-dimensional structure, is that even characterizing the first eigenvalue or eigenfunction is going to be a hard problem in geometry. So we can't rely on closed form expressions if we want our results to apply to general nonlinear geometries. And just to highlight a bit more why maybe existing approaches that could use asymptotic techniques may not work so well in this setting, if we try to formally write down an inverse for the certificate problem, so applying a formal inverse for the integral operator to this initial random error, what we see in this eigenbasis expansion is that what we need to prove that this quantity has a small norm is both a characterization of the eigenvalues as well as precise alignments between this initial random error and the eigenfunctions. So it doesn't feel like it's going to be sufficient here to proceed with asymptotic characterizations of the spectrum of these eigenfunctions. In particular, we need a more direct approach. And what we leverage in the paper is just a couple of qualitative insights, and we see how far that takes us. So what we find experimentally is that this kernel theta decays as you increase the angle, as you move away from zero angle. And as you increase the network depth, this decay gets faster and faster. So at right, I'm just showing this rotationally invariant kernel plotted over a chart for the two sphere at different depths. And we have this sharpening effect. So I've normalized it as well, but with this normalization, sharpness comes through. So we will try to exploit this property, and we will in our analysis by saying, okay, so if this kernel concentrates, sharpens as depth gets larger and larger, maybe we can use depth as an approximation resource in order to approximate this neural tangent kernel operator by a convolution operator on the manifolds that's in particular localized, so compactly supported. I'm defining this operator hat m sub r here with a parameter r that we should imagine is just a sufficiently small number. And what I've done that's different from the neural tangent kernel is I've changed out the domain. So I've localized it as well. I'm not using the angle in the definition of this operator that I'm applying the kernel to. I'm using the intrinsic distance as well. So in our analysis, we proved that there's a suitable approximation property between this operator and the initial neural tangent kernel. And that allows us to solve the certificate problem modulo, sort of working out a lot of the reductions I hinted at before. So the main result we get, so if L is sufficiently large relative to the geometric properties that appeared in the main theorem, then we have a certificate of small norm. In particular, the norm can be sort of controlled using the depth in a very weak sense that satisfies our approximation guarantees. So that's the depth story that I have. Just concluding with a couple of remarks. So I hope that some of these tools may be more broadly useful. Our concentration tools, these analyses, they're somewhat intricate, but they only use the fact that in the initial random neural network, the structure is compositional. At each layer, you're injecting sort of independent randomness by multiplying the previous features by a random linear map. So I think these techniques can be applied more broadly to get good rates in other architectures as well. And the localization analysis can be useful as well because it allows us to proceed in the NTK setting without having a specific diagonalization for the kernel. I think this may be useful more broadly and for higher dimensional geometries and maybe other kernels as well. And although what we're doing here is admittedly very rudimentary, we're sort of in the long term hoping that we're building up towards some kind of a toolkit that helps us to analyze theoretically training and optimization and generalization of deep neural networks instead of just focusing on the shallow case. Okay, so I'm a little bit over, but thank you for listening, and thanks one last time to my collaborators.